Hey, what's up? It's your old pal, Mr. Cook. We're going to work on this Unit 4, Part 2 test review. So in a previous video, I had gone over how to tell which method to use in which case. And you should watch that first just so you can see like which method to use. Because identifying which method to use is going to be like, majority of the points using the right method to find the integral. So this is just one video going over one of the methods. I'm going to be focusing on the trig identity problems first. On this one. So here are the identities that you're going to want to know. You're going to want to know the Pythagorean identities. So sine squared of x plus cosine squared of x equals 1. And then also the power reduction identities. So if you have sine squared of x, it's the same thing as saying 1 minus cosine of 2x over 2. And cosine squared of x is equal to 1 plus cosine of 2x over 2. Now with the Pythagorean identities, you want to know those because, well, specifically sine squared plus cosine squared equals 1, because it opens up like a bunch of other identities. Like if you were to divide sine into all these, you get another identity from it. And you also get to use this with the trig substitutions too. It's a nice identity to know. Because sine squared over sine squared becomes 1, cosine over sine becomes cotangent, and 1 over sine squared becomes cosecant squared. And then you get the last identity by dividing everything by cosine squared. So sine over cosine is tangent, so tangent squared. Cosine over cosine is 1. And 1 over cosine is secant, so that becomes secant squared. So these identities are really, really helpful to know, for these problems because you're just going to be substituting this stuff in pretty regularly. Okay, with that being known, now let's take a look at the problems. See the first one, trig identity. Here we go, number 23. So, so for this one, sine to the third and cosine to the fifth, the main objective is that like most of these trig identities are just going to use a u sub or maybe a really easy u sub to solve. But you first need to use some identities to utilize the u substitution. So with number 23, I've got sines and cosines. So here are two routes that I could go. I know I'm going to have to use a u sub and some identities here. And here's why. If I let u be equal to sine of x, then du is equal to cosine of x dx. And if I start to do the u sub in here, some bad stuff starts to happen. So if I replace the sine to the third with u, that becomes u to the third. So far looking good. And then I need a cosine of x dx to become du's. And I get a cosine from this one, right? Because cosine to the fifth is the same as saying cosine to the fourth of x times cosine of x. And then I've got that dx there. So that cosine of x dx is like, right there, it becomes a u. So cosine to the fourth is still left over, though. That's like kind of a problem. But the nice thing is this. You can use identities to simplify this in terms of sine. That's the idea. You want to get it in terms of sine to make the expression a lot easier. So here's how I would do it. Cosine to the fourth power is the same as saying cosine squared to the second power. And I know that there's this nice identity that relates sine to cosine. Sine squared of x plus cosine squared of x equals 1, the Pythagorean identity. So if I were to solve for cosine squared in this case, if I subtract it from both sides, I get cosine squared. I'll just subtract it. It's cosine squared of x minus sine squared of x. Cosine squared of x is equal to 1 minus sine squared of x. And since I know that sine is equal to u, I can turn this into 1 minus u squared. And that's exactly what I want to do with this. Cosine squared, I'll replace with 1 minus u squared. And all of a sudden, this cosine to the fourth, which I turned into, cosine squared squared, now can just be replaced with 1 minus u squared squared. And now this is all in terms of u, so I can finally do my u substitution, and all is right with the world. So first things first, I would like distribute this stuff out. So the quantity 1 minus u squared can be rewritten like this: 1 minus 2u squared plus u to the fourth, and then du. And then I distribute my u to the third in all of those things. So I get integral u to the third minus 2u to the fifth plus u to the seventh power du. And then I just use power rule on all this stuff. So I get 1/4 u to the fourth minus 2/6 u to the sixth, and then 1/8 u to the eighth, and then plus c. Then I'd replace that stuff back in. So I'd replace all the u's with signs. 1/4 sine to the fourth of x minus 1/3 sine to the sixth of x plus 1/8 sine to the eighth of x plus my constant. Okay, so there's 23, 29, and 30 are both going to be, now I wouldn't actually use the Pythagorean identities here. Here's why. Sine squared would be the same thing as 1 minus cosine squared, but if I just, use 1 minus cosine squared for this, it doesn't actually like make the expression any easier. So it's kind of like a lateral move instead of solving it or making it any easier with a u sub. So instead what I'm going to use is the power reduction rule. Okay, so sine squared is the same as saying 1 minus cosine of 2x over 2. And this makes a world of difference because I can just split this apart. So, I can make that into two fractions, 1/2 and cosine of 2x over 2. And then on top of that, I can just move this 1/2 out front here. And now I do my antiderivative. So antiderivative of 1/2 dx is going to be 1/2 x. And then now I'd have to do like a simple u sub on this one, let u be equal to 2x. That means that du is equal to 2 dx. So I have to get like a 1/2 out front. I gain a 1/2. So I get a 1/2 from this, and then another 1/2 from this. And then antiderivative of cosine is just sine. So sine of 2x, and then plus c. And then here's what's interesting about cosine squared. If you use the power reduction rule, this just becomes a plus, and then that becomes a plus, and that becomes a plus. So that's like the antiderivative for that one. Okay, so that's up to number 30. Next up is number 33. Yeah, 33. And this one's super easy. 1 minus sine squared, if I use Pythagorean identity, that's the same thing as saying cosine squared of x. So cosine squared of x over cosine of x dx. The one cosine can cancel from the top and the bottom. And then the antiderivative of cosine is just regular old sine. So sine of x plus my constant. And that's about like the level you should probably expect to see on a test. Okay. Let's see here. What else do I want to do here? So next one. Cotangent, cosecant. This one I think is kind of interchangeable. Let me double check. Yeah, it doesn't matter if you use u for cosine or cosecant or u for cotangent. Yeah, so you can pick either one. I'll let u equal cotangent, for example. Then du is going to be equal to, let's see, derivative of cotangent is negative cosecant squared of x dx. So let's replace that stuff in there. So for number 35, if I use my u substitution in here, I get, let's see, well, I need a cosecant squared dx from this. So if I take a cosecant squared from that, that's the same as cosecant squared times cosecant squared. And then I still have that cotangent to the third of x dx. Well, I've got a cosecant squared and a dx. That's this stuff. So that becomes a du, but I also got to have that negative. So I'm going to move the negative out front. So here's what I have left. Cotangent to the third becomes u to the third. But I still got that stupid cosecant squared, don't I? So what do I do with it? So this is where it's helpful to use an identity. So remember that one of the Pythagorean identities that we had was cotangent squared of x plus 1 is equal to cosecant squared. So I can just replace the cosecant squared here with cotangent squared. And why is that helpful? Well, cotangent is my u value. So this is the same thing as saying u squared plus 1. So that cosecant squared, I can just replace it with u squared plus 1. And now this problem gets really easy. I can just distribute in that negative u to the third. So I get a negative u to the fifth minus u to the third du. And now I would just use power rule. So I'd get a negative 1/6 u to the sixth minus 1/4 u to the fourth plus my constant. And then I'd backward substitute. So I'd plug back in the cotangents. And I would get a negative 1/6 cotangent to the sixth of x minus 1/4 cotangent to the fourth of x plus my constant. And that'd be it for this one. Okay, and then let's see, do I have another trig identity one? Yeah, number 37 it looks like. All right, 37. Okay, yeah, right off the bat. Tangent squared plus 1, that's the same as saying secant squared. So I can replace this with secant of x over secant squared of x dx. And one of the secants will cancel out in the top and the bottom. And 1 over secant of x is just cosine, so that just becomes cosine. And the antiderivative of cosine is going to be sine. Oops. So sine of x plus my constant c. All right, easy enough. Let's see, do we have any more identities? Yeah. All right, 47. So if you've got like a bunch of trig ratios, sine, secant, tangent, anything more than like 2, typically that means you just got to kind of mess around with the ratios to combine them together. And since all secants, tangents, cosines, all that, cotangents can be replaced with sines and cosines, that's what you should do here. So secant, remember, is the same thing as saying 1 over cosine. So that's what I'm going to replace it with. And tangent, I didn't talk about this one earlier, but this is just one you should know from algebra 2. Tangent is the same thing as saying sine of x over cosine of x. So that's what I'd replace all that stuff with, those two, secant and tangent. Like what I used to tell my honors algebra 2 kids, I would just tell them, hey, if you need to evaluate something that's got more than 2 ratios, make everything in terms of sines and cosines, and then try to use algebra to reduce it. And that's what I'm going to do in this case. So that sine, I'm just going to keep it as is, so sine of x. But then the secant, I'm going to replace it with 1 over cosine of x. And then that tangent, I'm going to replace that with a sine of x over cosine of x. Now, when I have a fraction and I'm dividing my fraction, right, what I would do is I'd multiply by the denominator's reciprocal. And that's what I'm going to do here. I'm going to replace that or rewrite this so it becomes sine of x plus 1 over cosine of x. So the numerator times the reciprocal of the denominator, cosine of x over sine of x, and then dx. And then what I would do is I would distribute this in to both of these. And here's what I'd end up with. I'd get sine of x times cosine of x over sine of x. Notice the sine of x will cancel out. Plus, and then I've got 1 over cosine of x times cosine of x over sine of x. And notice that the cosines will cancel out there. Yeah, so what do I end up with here? Well, the sines cancel, so I just have a cosine. Then the cosines cancel, so I just have a 1 over sine. And then 1 over sine of x is the same as saying cosecant. And now all of a sudden these are really easy. These are just memorized rules. So the antiderivative of cosine is sine. The antiderivative of cosecant is a negative natural log absolute value of cosecant of x plus cotangent of x plus c, my constant. All right, so that's all the trig identity problems for the worksheet. So I guess I'll stop the video here and move on to a different method. So I hope to see you in the next video. If you need help on anything, just make sure you reach out to your calc teacher. Thanks, and I'll see you in the next one. Bye-bye.